So in this lecture we introduce Dedekind domains and prove an important result about unique factorization of ideals in Dedekind domains. So first, what is a Dedekind domain? A Dedekind domain is an integral domain R such that R is Noetherian, R is integrally closed, and every non-zero prime ideal is maximal. So some examples are integers, this complex I, so that is square root of -1, which we are writing as red I, this attached to integers, this ring of polynomials in one variable where this k is a field, and discrete valuation rings. So there is a very tight connection between Dedekind domains and discrete valuation rings. So the primary reference, everything here has been taken from the notes of Milne. These are online. This is an algebraic number theory notes by Milne. So the first major result we want to prove about Dedekind domains is unique factorization of ideals. So let A be a Dedekind domain, then every ideal A which lies in this A, this can be factorized into unique prime ideals like this. So A, you can write it as P1 R1 multiplied by P2, exponent is R2, all the way to Pn, exponent is Rn, where each of these exponents is greater than 0 and each of these pi's are distinct. So with each pi as a distinct prime ideal. So to prove this, we will need three lemmas, which we will prove these three lemmas in the next lecture. So here we are just noting it down so that we can prove this theorem. So lemma 1 is that every ideal A in the Noetherian ring A contains a product of non-zero prime ideals. Lemma 2 is, so you are given A and B, two ideals, and these two ideals are relatively prime to each other. So that is, sum of them would generate the entire ring A. So these two are relatively prime ideals in some ring A. Then you raise A to some power m and B to some power n. Then these two would be relatively prime, where this m and n are natural numbers. So third lemma which we will use is this. So say you have P, which is a maximal ideal in a ring A. So you can always localize with respect to this maximal ideal. So now you consider the corresponding local ring, this AP, corresponding to this maximal ideal. So maximal ideals are prime, so therefore you can always localize. Now this local ring has a maximal ideal which is just PAP. This we denote by this Q here. So then we have an isomorphism. From A you modulo out P to the m. This is isomorphic to take the local ring and then modulo out with its maximal ideal to the same power. So you have P to the m here, you have Q to the m here, which is its maximal ideal here. So this is important because from this structure we are passing to this structure which is a local ring. So this is a local ring and we are just talking in terms of the maximal ideal of the local ring. So this power here gets transferred here. So we have these three lemmas. Now we can prove this theorem. So first lemma says that every ideal A in this ring A, which is Noetherian, will contain a product of non-zero prime ideals. So we are working in the Dedekind domain A, so therefore by our definition it is Noetherian. So you have this ideal A, so every non-zero ideal A contains a product of prime ideals. So this ideal A contains another ideal B, which is actually a product of prime ideals like this, P1 to the R1 multiplied by P to the R2 all the way P to the Rm, where B is an ideal in A itself. Now we suppose that all pi are distinct. So now from the Chinese remainder theorem you can say A modulo B, this is iso to A over P1 R1 all the way to A over Pm Rm. So notice that these are prime ideals, and in a Dedekind domain prime ideals, there is a prime ideal which is maximal. Now since prime ideals are maximal in Dedekind domains, so all these prime ideals are co-prime to each other because they are all maximal. None of the prime ideals contains another prime ideal, so we do not have a chain of prime ideals, one containing another. So all of these prime ideals are co-prime to each other, and by lemma 2 you can say their powers are also co-prime. So if A and B are co-prime, then their powers are also co-prime. So therefore you have this co-primeness here, and therefore you can use Chinese remainder theorem here. So by Chinese remainder theorem you can write it like this. Now you can use lemma 3 here. So corresponding to every a pm you can write localize it with respect to the prime in the denominator, and then you take the same power here. So you localize it with respect to prime in the denominator. You have ap1 corresponding to it, this you take its maximal ideal q1, which you raise to the same power here. So this lemma 3 works right here, and you can do that for every such thing. So you have this decomposition here for a modulo b. So now we use a very important fact. So let A be a Noetherian integral domain. Then A is Dedekind if and only if this A localized at P is a discrete valuation ring for every non-zero prime ideal P in A. So this direction is easy. To show this direction requires a lot more work. So this we are going to use as a fact here, as a black box, but this you can say is a big theorem, and it tightly links Dedekind domains with discrete valuation rings. So for our purposes we just require this side implication. So since we are working with the Dedekind domain, if you take this A localized at a prime ideal P here, it will be a discrete valuation ring or a DVR. So now instead of this ring A modulo B, you can consider this ideal A modulo B, because A contains this P. So A modulo B. So denominators you take as such. So these denominators we copy as such here. And here this A we are considering in each of these localized rings right here. So this A you consider this extension in AP1, and for the second factor you consider this extension in AP2 all the way to APM. But each of these are DVRs, so each of these are discrete valuation rings. So recall that discrete valuation rings, they are made up from uniformizing parameters. So these uniformizing parameter, there is some uniformizing parameter which generates the ideals. So it generates the denominator, it generates the numerator as well. So whatever generates the denominator, the uniformizing parameter, it also generates the numerator. So you will have this q1 r1, and then you will have q1 s1 in the numerator, because we are working in a DVR. So you will have something like this. So the denominator and the numerator will look similar because both of them are generated by a uniformizing parameter. So you have this q1 s1 in the numerator, and you keep on going it like this. You have some qm sm in the numerator, precisely because we are in a DVR. This is the maximal ideal to some power in DVR, because this is an ideal which is contained in this local ring here. Local ring is a DVR, so this is generated by uniformizing parameter, this is generated by the uniformizing parameter. So now you have to just notice that SI is less than equal to RI. So because if it is greater than RI, then obviously everything would be 0. So A contains B means that A has lesser power compared to the ideal in the denominator. Yeah, that is it. So this is just follows from the property of A containing P. Otherwise denominator will divide the numerator and you will just get 0 everywhere. So now from lemma 3 we can say that you have this isomorphism. So you could have, to get this left hand side, we are going to, so left hand side we will write some product like this, and right hand side we just copy this down here. So you just copy this entire thing down here. This is right hand side. So this P1 S1 times P2 S2 all the way to PM SM, this will get mapped to something like this, and this is precisely from here, because this each of these P's gets mapped to the some Q same power in the localized ring. So once you localize it, each of these PM is getting mapped. There's an isomorphism here if you localize things, and this is coming from here, which is a localized ring here. So we have this isomorphism here. So each of these will correspond to Q's here. So that's why we have Q1 S1 all the way to QM SM. So now you have this getting mapped to here and this getting mapped to here. So right hand side is the same, so it has to be the case in ring A modulo B. A is just P1 S1 all the way to PMSM, and there is one-to-one correspondence between this ring with the ideals which contain B and ideals of this ring. So ideals of this ring will also contain B and A contains B, like this. So essentially what we are saying is that A essentially comes to be of this form: A P1 S1 all the way to PMSM, where obviously each SI is less than equal to Ri. So if SI is less than equal to Ri, it will automatically contain this ideal B here. So we have been able to show that this ideal A, which we started with, this has this form. So here we are writing S1 all the way to SM, and here it is R1 to R, and it really doesn't matter because we could have chosen S1 to SM here and put R1 to RM here. So I'm just following the convention as in the online notes, but you see this S1 to SM you could have taken as R1 to RM. So this is just a general product, but here we have been able to show that every ideal A will split like this. So the only thing we have to do is that we could have taken this product as P1 to Pn and then S1 to Sn, and then just changed R and S to get this thing right here. So now we have to show the uniqueness. So we said it can be factorized, but we have to show that it can be factorized into unique prime ideals. So now we talk about uniqueness. So suppose there are two factorizations of this ideal A. So this ideal A, you can write it as P1 S1 all the way to PMSM, and also from P1 to the T1 all the way to PMTM. So you can do two such factorizations. So first thing you do is you have the same number of prime factors on either side. So say if you have some p to the k with some power tk here in this factorization, and this pk does not occur here, you put this pk here and raise it to the power of 0. So you have the same number of prime factors on either side. So that you can do. So now what you do is you take this A and consider its extension in this ring API, which has maximal ideal QI, and which QI is nothing but is PI API here. So now we have seen that this is a DVR. So if you extend it in this, it will be of this form: QI to the power SI, where QI is the maximal ideal of our DVR. And this is in two forms now. If you take corresponding to prime PI here, you will raise to the power SI here. If you take corresponding to prime here, localized with respect to some prime here, because this has to be localized with respect to every prime. So we are just generalizing by taking with respect to PI here. Then you can take with respect to same PI here, because you have the same number of prime factors on either side. You will get something like this. So you can say now SI is equal to TI, because these two are equal, and QI is a maximal ideal. So QI is a maximal ideal because this is a local ring. So this is a maximal ideal, and therefore these two are equal, so their powers have to be equal. So that gives us the factorization uniqueness of our factorization. So we are done with this theorem, and the most important part of the theorem is the use of this fact. So every time you talk about Dedekind domain, one has to think of the corresponding DVRs, and this you can also think of as a starting point of schemes. You have a domain, and you have this AP as stocks. So you have this corresponding between this global ring A, and locally it is stocks with discrete valuation rings.